Hello, I'm Fabrizio Pastore from the SNT Center of the University of Luxembourg, and I am going to present our journal first paper about mutation analysis for cyber-physical systems, scalable solutions and results in the space of domain. This is joint work with Oscar Corneo and Lionel Briand. This is one of the results of our project about the automated assessment of quality assurance procedures for software running on space systems and also automated improvement of these procedures. This is a project that involves GomSpace Luxembourg, which is a developer of nanosatellites, and LuxSpace, which is a developer of microsatellites. Our results are available also on our website. Software has a prominent role in space systems, and consequently, software failures have high impact, ranging from explosions to loss of a large amount of data. Therefore, it is important to ensure that software is appropriately verified and validated. But what are the methods that are commonly adopted for that? Well, software testing is prevalent. To give you an idea, this is a word cloud that I generated from one of the quality assurance standards for space software, and you can see that the only technical keyword that you can for verification and validation that you can notice in this word cloud is test and testing. But how to ensure thorough testing, which is our objective? Well, a well-known way to assess that the testing is performed appropriately is mutation analysis. It consists of automatically generated faulty versions of the software under test that are called mutants, and mutants are tested with the test suite for the software under test. The mutation analysis metric is the mutation score, which measures the percentage of mutants leading to a test failure. Ideally, you want to achieve 100% of mutation score. But this is not always possible because of the presence of equivalent mutants, which are mutants that behave as the original software, and redundant mutants, which are mutants that are similar to each other. And both together, they affect the quality of the mutation score as a quality assurance metric. Then there is another problem that affects the feasibility of mutation analysis, and it is scalability. In fact, when you generate mutants automatically, they may be many, and when test suite takes a lot to execute, which is the case, for example, for space software and in general for software running on cyber-physical systems, then it becomes very expensive to perform mutation analysis. So we aim to address these problems in our project. Of course, these are already, let's say, tackled in the literature, but the current solutions do not apply well in our context of space cyber-physical systems. For example, first of all, there are many techniques that perform optimizations to address these problems, but they had never been tested altogether in an integrated pipeline. Concerning some scalability solutions that are mutant schemata and split stream execution, they are infeasible to apply in the presence of hardware emulators, which are instead normally adopted for space software and for software running on cyber-physical systems, because this software is compiled for specific architecture and then you need an hardware emulator to test it. There are mutant sampling solutions to reduce the amount of mutants to test, but they either provide no accuracy guarantees or they require too many mutants. We have test suite prioritization solutions to speed up the identification of let's say, test cases that kill mutants, but they make assumptions on the test length. They are applicable only for unit tests, which are not always available in our context, or rely on an expensive data flow analysis that we cannot perform for these systems. Concerning the detection of equivalent mutants, one solution is to rely on symbolic executions, but it is infeasible with large systems like this one, because you need to model all the communication channels, which is infeasible, or these systems include floating points. arithmetics, and it is not supported by state-of-the-art tools. Then there are solutions that rely on dynamic analysis, but they collect too much data for being applied in these systems. Then the last point is about redundant mutants, which is, let's say, still an open research question. One of the latest work indicates that it will be better to keep all the subsumed mutants, but improve the test suite to distinguish them. So in our work, we don't discard subsumed mutants, we just discard duplicate mutants, but we do not deal with the generation of test cases automatically. We developed a pipeline in a tool set that we call Mutation Analysis for Space Software, MAS, and I'm going to present it now. In the first step of the pipeline, we collect code coverage for the original software. This because we are going to create mutants only for the statements that are actually tested by the unit test suite. Here the idea is that these systems are normally well tested. They need to fulfill some statement coverage criteria, and if something is not covered, then there is a good reason. For example, because the test suite is a test suite running with simulators, and certain portion of the code can be executed only with hardware in the loop. Then we create mutants. We create mutants following, the literature. So we rely on the sufficient set, the deletion operator set, and the LVR operator. Then we compile mutants, and we keep only the ones that are successfully compiled. Then we remove equivalent and duplicate mutants based on compiler optimizations, which is standard practice. So the idea is that equivalent programs may lead to the same executable after a compiler optimization. So what we do is that we compile the original software and every mutant multiple times, once for each optimization option, and then we compute the hash summary of the generated executable. And then we compare the hash summaries to identify the equivalent and duplicate mutants. Then what we do is to sample mutants, and the mutant sampling is one of the key contributions of our work. Let's assume that the mutation score for your system, when you consider all the mutants, is 65.36%. When you perform mutant sampling, what you can observe is that depending on the number of mutants that you sample, you may end up getting close to the actual mutation score with a little bit of variation. Of course, if you do the experiment multiple times, you may observe, kind of fluctuations between the experiments. But the key point here that you may notice that what you want to do when you perform mutant sampling is basically to stop when you are close enough to the actual mutation score. So what we did is to develop a method to determine when we are close enough to the mutation score. And this method is based on the computation of the confidence interval. A confidence interval captures a range that has a probability, for example, 95%, of including the estimated value, which in this case is the mutation score. So the mutation score can be represented by this range that has a lower and upper bound. And normally what is returned to the end user is the value in the middle. Then what we applied to stop sampling is a fixed width sequential confidence interval method, which is a statistical method. So basically it means that we stop sampling when the difference between the upper and the lower bound is below a given threshold. For us, the threshold is 10 percentage points. And we use this value because it means that the difference between the mutation score that is returned to the user, so the value in the middle of this range, and the actual one will be at most 5 percentage points, which means that maybe we return 61% and then the actual mutation score is 65%. And we think that this difference is acceptable. To have an information that is accurate enough about the mutation score of your software. And assuming that the mutation score follows a binomial distribution, we rely on the Klopper-Persson method for the computation of the confidence interval. So what we do basically is that we sample mutants, then we execute test case on the sampled mutants, and then we evaluate the mutation score confidence. And if it is not short enough, the confidence interval, then we sample another mutants and we go ahead like this till we obtain a confidence interval that is small enough according to our criterion. But actually what we do is not to execute all the test cases. What we want to execute a subset of the test cases to speed up testing further. I will explain how we select this subset later. But the point is that since we execute a subset of these test cases, we may exclude the test cases that kill the mutant. So what we did in our work is to introduce a confidence interval correction factor. So basically, without going too much in the detail, what you may observe is that the mutations, when computing this confidence interval for the mutation score, you need to take into account for the proportion of mutants that you consider live by mistake. Okay, so when I say live mutants, is a mutant that was not detected by the test suite, therefore that was not killed by the test suite. And this proportion of mutants can be estimated, and we do it, details are in the paper, and therefore we can transform our formula for the computation of the confidence interval like the following, so that we take into account for the estimated lower bound for the mutation score and the estimated lower bound for this proportion of live mutants, and we do the same for the upper bound. Basically, at this point, we have a correct estimation of the confidence interval. What we want to do then is to prioritize the test cases, okay? So how we do it is that we rely on the statement coverage, because this is a state of the art somehow. And for test suite prioritization, basically we introduced a greedy algorithm that selects first the test cases with the larger distance from the closest test case that was already selected. So basically we introduce let's say in the test suite to be executed test cases that largely differ from each other, which means that they may test the software with very different values, and therefore they are more likely to kill the mutant. And then we stop considering test cases when the remaining test cases have a distance of 0 from the test cases already selected, which means that basically do not stress the software in a different way. When I talk about distance, I mean the cosine distance, because we have experiment with multiple distance metrics, and the cosine is the one that provides the best accuracy. Details are in the paper. Once we have executed our mutants with the prioritized subset and we have a good confidence interval, we are almost done, basically. The only thing that we want to do is to discard some equivalent mutants that may have been not discarded by the compiler optimization options, and to this end, we rely on the code coverage. For this, we are inspired by the work of Schuler. And basically what we do is we consider the code coverage for the original program, the code coverage of the mutant, and for all the test cases we compute the difference, the distance between this coverage information. And if for the pair with the larger distance, the distance is above a given threshold, we consider the mutant as being not equivalent, because it means that at least for a specific set of test inputs, it makes the software behave in a very different way than the original program. Okay? In our experiments, this distance is 0, which means that if the mutants for at least one specific set of inputs behave in a slightly different manner than the original software, then it is likely to be non-equivalent. And this is something that we have empirically evaluated after manually inspecting mutants, and details are provided in the paper. Once we have the set of killed mutants and the set of live non-equivalent mutants, we can compute the final mutation score. And then, of course, the live non-equivalent mutants can be provided to the engineer to inspect them and identify test inputs that kill them. Now, for the empirical evaluation. We considered these case study subjects, which are the control software of the ICSE satellite, which is a satellite that was launched on orbit in 2019. We have the network configuration and utility libraries that are used in GomSpace NATO Nano satellites, and we have a mathematical library for flight software that is provided by ESA. In our paper, we have a number of research questions that I cannot fully present today in this video, and I present just a subset of them. The first research question is about comparing our FSCI-based sampling with other approaches. So we compute the actual mutation score using all the mutants for the software under test. We compute then the mutation score obtained with different sampling methods, and we consider 100 executions for each. And the methods that we consider are uniform sampling, which means selecting 1-2% of mutants, uniform fixed site sampling, which concern selecting a specific number of mutants, and FSI-based sampling with different configuration for the confidence interval. Then we want to determine which approach configuration provides an accurate mutation score with the lowest number of samples. The mutation score is accurate if, for 95% of executions, the difference from the actual mutation score is below 5 percentage points. These are our results. What I plot here are the results obtained with different methods. For example, here is mutant sampling of 1% of the mutants, the number of mutants that this method lets, and the delta, the average delta that it is obtained for these 95% of the cases. What we want to obtain is a delta that is below 5. Okay? So we sort all the results based on the number of mutants that we have. And what you can observe, and we report in bold all the values that are below 5. What you can observe is that our FSCI-based method is the only one that provides guarantees about the results. It means that it is the only one that is always on top. In a couple of cases, we have other approaches that are a little better than our approach because they select a little fewer mutants with a delta that is still below 5, but our approach is the only one that is always among the top 2, let's say, and which means that it provides guarantees about the accuracy that we obtain. And this is an important result of our research. Then we wanted to evaluate which is the test suite optimization strategy that speed up more the mutation analysis process. And then what you normally do is to have a non-optimized mutation analysis process, which means that for each mutant you execute the test cases that, let's say, cover the mutant. The other ones, of course, cannot kill the mutants because they don't cover it. We include two optimizations, FSCI-based sampling and prioritize and reduce. And this leads to 3 possible configurations for our approach. So execute all the mutants and just apply prioritize and reduce. You can rely only FSCI-based sampling, which means that you execute less mutants, but you execute all the test cases for them. And then you execute FSCI-based sampling with the prioritize and reduce. And then we computed the time savings with respect to the non-optimized execution among 100 executions. So this is the execution time obtained for, without optimization, and it can be very large. So when we execute all the mutants and apply prioritize and reduce, we don't have, a big time reduction. The median is around 5%. Okay? But when we introduce FSCI-based sampling instead, the reduction is large, is 75% of time savings, okay? Which means that that is a very effective method. And when on top of that we also add prioritize and reduce, it is further reduced the execution time. So with the median is around 80%. So basically, our approach, you can see that it makes mutation analysis feasible also for a large software. For example, in the case of eSale, we go from 11,000 hours to 1,500 hours. Of course, you cannot run this execution on a standard desktop PC. You need more nodes, okay? And it will lead, for example, to 12 hours with 100 nodes for agreed computing infrastructure. But this is a cost that is, normal to take when you have such safety-critical systems. The last research question is just about a comparison of our mutation score that exclude equivalent mutant and the mutation score for a traditional process that do not exclude equivalent mutants. And of course, the mutation score that we obtain is higher. Here, if I want to report some more concrete results, what we noticed is that the mutation score reflects some imperfections of the test suite that we considered. The test suite that we considered in our analysis are test suite for the software in the loop testing, which means that this hardware is simulated. And so several features were covered with hardware in the loop testing, which means that the engineers forgot to add, for example, oracles for the software in the loop testing. And this is a pitfall actually of the problem, because it means that they will end up noticing implementation problems too late when they are already testing with the hardware. And also they were missing cases for exceptional and unusual cases. Further, we also identified problems with the MLFS case study, which achieves MCDC. And here the problem is that, our deletion operators show that there are limitations in the test input partitions covered. For example, they don't test a Fourier transformation with all the set of values that are useful to understand if they are missing some operands. To conclude, we addressed the problem of assessing the quality of test suite for cyber-physical systems, and in particular space cyber-physical systems. We provided a mutation analysis pipeline that is scalable and can be applied not only to space software, but in general to other types of systems that present similar characteristics. Our results confirm the scalability of effectiveness of the approach. In particular, the FSI-based sampling approach is accurate and introduces large time savings. And also, we have noticed that mutation analysis enables to detect test suite pitfalls for these safety-critical systems. Our results and these and other ones are available on our website. Thank you for listening.